Thank you very much, Jesse, for a nice introduction. Let me share my screen. So let me make it bigger. Can you see my screen?
Yep, it looks good.
Okay, thank you so much again for providing me this opportunity to present this ion beam cooling with JSPEC. This is mainly based on my research work during my PhD. I have divided this presentation into two parts. First part is about general introduction of beam cooling and electron cooling. And I will give an example of dual energy storage ring electron cooler, which is my main PhD project that I was working, and some electron beam parameter and proton beam parameter we use to run JSPEC cooling simulation. And the second part will be the demonstration of JSPEC simulation using SIREPO. I will demonstrate how to do simulation in JSPEC using SIREPO to cool to 75 GeV proton beam. So basic introduction of beam cooling. So why we need beam cooling? The beam cooling is synonymous with a reduction of beam temperature. Yes, cooling means just to lower the temperature of something. So in case of electron beam, for example, electron beam with energy order of few MeV undergoes synchrotron radiation effects and cools to a lower temperature. But heavy particle beam like ions beam or proton beam, the effect of synchrotron radiation damping is not significant, even in the energy range, the order of hundreds GeV. So we need some mechanism to cool heavy particle beam or like ion beams or proton beam. So we need a method to cool them. So here in this presentation and in demonstration, I'm going to present the electron cooling to cool heavy particle beam, especially proton beam at 275 GeV. The application of beam cooling finally results in the reduction in the phase space volume of heavy particle beam, and that means beam cooling decreases the beam size and emittance and decreases the energy spread. This energy spread is longitudinal emittance, and this other beam size is transverse, which means horizontal and vertical emittance. And also it increases the intensity of beam and helps to accumulate the many particles in the given phase space volume, and also increases the beam lifetime. So during the injection of beam in a storage ring, there are many factors that increases the beam size. For example, interaction of beam particle within a bonds itself, which we call intrabeam scattering. Also, those particles interact with the rest gas, some internal targets, and there is also some injection error, which eventually increases the beam size and increases the beam emittance. The goal of beam cooling is just to counteract the degradation of beam quality due to these factors and to lowers or to control the beam size or emittance, which eventually helps to enhance the luminosity in a collider. So among the different methods in this presentation, we are going to discuss and present electron cooling, which means we use cold electron beam to take heat away from the hot heavy particle beam. So here is in a picture in example of electron cooling. You can see here electron beam coming from the source electron gun, which is at lower temperature, and that is going to interact with the heavy particle beam in this straight section that takes heat away from the heavy particle beam. So this electron cooling was given by G.I. Boudker in 1966, which is based on the law of thermodynamics. The basic principle of thermodynamics is that heat transfer takes place from a system at a higher temperature to a system at the lower temperature until there exists an equilibrium temperature between two systems. Here, electron beam is one system at lower temperature, and heavy particle beam is another system at higher temperature. So to make simplicity, I'm taking an example of proton beam. So electron beam coming from electron gun and proton beam coming from the proton storage ring interacts in the straight cooling section, where electron beam taking heat away from the proton beam finally reaches to the collector, that the proton beam giving heat to the electron beam circulate in the proton storage ring, and the process repeats. New fresh low temperature electron beam coming and interacting with the proton beam, taking heat away from the proton beam, and this exists until there exists an equilibrium temperature between electron beam and the proton beam. So here is a simple mathematical formula that at equilibrium temperature, the temperature of proton beam equals the temperature of electron beam. And we know that mass of the proton beam is almost about 2000 times bigger than the mass of the electron. And due to this cooling effect, the angular spread of the proton beam is reduced by a factor of 40, which means that beam temperature reduces, that beam size reduces. In this luminosity formula, you can see in the denominator, there is sigma x asterisk and sigma y asterisk. These are the proton beam sizes, horizontal and vertical proton beam sizes in the interaction point. So reducing these beam sizes increases the luminosity in a collider. This is the main goal of a collider. This luminosity is a figure of merit in a collider. And this luminosity also depends on N1 and N2, where N1 and N2 are the number of colliding particles for two different bunches. For example, in an electron ion collider, N1 may be for the electron and N2 may be for the ion colliding at the interaction point. This F is a repetition frequency, and M is the number of bunches. So the main goal of cooling is to reduce the beam sizes to enhance the luminosity in a collider. Based on this principle, I'm going to give an example. Before that example, I just want to give a basic introduction of JSPEC, which stands for Jefferson Lab Simulation Package for Electron Cooling. And it is an open source C++ package for this cooling simulation. Here are some references that you can go through. These references that explain more about JSPEC, how to do JSPEC simulation, and what are those parameters that we need to understand during the simulation. So here is an example. This is dual energy electron storage ring cooler. This example is given because this is one of the possible design we were studying for electron ion collider cooler concept, and it has two rings. One is low energy ring, another is high energy ring. So to cool to 75 GeV proton beam, we need 150 MeV electron beam in the cooling section, because to get the more interaction between electron beam and the ion beam, their longitudinal velocities should be close to each other. That gives a strong scattering force between them during the interaction. So in this example, 150 MeV electron beam is injected in the low energy ring. That is accelerated by the RF cavities, go to the higher energy ring, which is 500 MeV, and that 500 MeV going through this arc section undergoes synchrotron radiation damping effect, and due to that, this electron beam cools to a lower temperature. And we use the same RF cavities, but we apply the accelerating phase. So the electron beam at lower temperature from high energy ring comes to the low energy ring and interacts with the proton beam, which is not shown here, but which is adjacent to this ring. So cooling interaction happens in this cooling solenoid. This is an example of magnetized cooling. So we use solenoid magnet with certain magnetic field, and here that enhances the cooling interaction between electron beam and the proton beam. So for the electron beam, equilibrium emittance is achieved under the combined effect of intra-beam scattering, synchrotron radiation, and quantum excitation. So I don't want to go detail in these terms, but the point here is electron beam parameter, especially this emittance, which means temperature, transfer temperature, and longitudinal temperature, is achieved from this cooler, and these temperatures are necessary to run JSPEC simulation. So here is a table that accounts for those parameters for electron beam and also some parameter for the proton beam. You can see the transfer temperature, which is about 9000 eV, and longitudinal temperature, which is about 0.27 eV. This is for electron beam. These are calculated using the formula in the right side. As I already mentioned, this is an example of the magnetized cooling, but we can also do unmagnetized cooling using JSPEC simulation. So the transfer temperature depends on this Larmor emittance. because it is an example of magnetized cooling. An electron beam going through the solenoid undergoes a lot more precision, and we need this lot more emittance to calculate the transfer temperature. And longitudinal temperature depends on this energy spread, and we have the values of energy spread in the cooler, which is 7.4 10 to the power minus 4. And using this, multiplying this by the rest mass, we can calculate the longitudinal temperature. In the same way, we have the proton beam parameters. The proton energy is 275 GeV, and the corresponding proton beam parameters are listed here. So we use these values to run cooling simulation. Before going to cooling simulation, I want to show some plot, some understanding what happens during the cooling interaction. So with these 275 GeV proton beam, you can see in this plot, which is a emittance growth of 275 GeV proton beam. These are horizontal, vertical, and longitudinal emittance of the proton beam in the absence of cooling. These are increasing, which is due to the intrabeam effect in that proton beam. So our goal is use that electron cooling principle to lower these emittance of the proton beam. So here is how JSPEC in Sireppo look like. You can see it has a different section: ion beam section, cooling and intrabeam scattering section, rate calculation section, ring section, and cooling electron beam section, and another cooler section. So I will go in details how to give input during my demonstration part. So this is just an example. How does JSPEC in Sireppo look like? And here is the results of cooling simulation. The first plot is, you can see the longitudinal emittance, which is delta P over P, is decreasing, but horizontal emittance, which is epsilon X, and vertical emittance, which is epsilon Y, is increasing. So this is in the absence of dispersion. So cooling is a dynamic process. You cannot get equal cooling in all three directions. So we need to introduce some dispersion in horizontal and vertical direction, including this dispersion redistribute the cooling in horizontal and vertical direction from longitudinal direction. So in the right side, with introducing dispersion of 2.5 meter in horizontal and 0.5 meter in vertical, with introducing coupling factor of 0.2, you can see the horizontal, vertical, and longitudinal emittances all are decreasing or somehow constant. So this means there is a cooling effect of the proton beam to 75 GeV proton beam using the parameters presented in the previous table. From this phase space, it is also clear that the 275 GeV proton beam phase space reduces after the cooling effect. There are two colors. One is initial and the final. You can see this final beam phase space is shrinking all in 6 direction. That indicates that the proton beam is cooling after interacting with the electron beam. So here are some references. I will come later. So this is the basic idea. I want to save my window. Sorry for that. So here, this is JSPEC in Sireppo. If you log into Sireppo, then you can get a lot of course there, and just click on the JSPEC. When you click on the JSPEC, you can view this window here. So it has many sections. First section is the ion beam section. I'm taking the proton beam, but you can choose different ions. This is the proton beam, kinetic energy for 275 GeV proton beam. RMS momentum spread is given here, 6.6 10 to the power minus 4. We take 6.9 10 to the power 10 number of ions, and we use the bunch beam. Bunch length is about 6 centimeter. And also we have these values, normalized emittance in horizontal and vertical. So these parameters are taken from EIC CDR published in 2021. And another section is cooling and intrabeam scattering. We give the number of samples ion 10 to the power 4. This is the way how you divide or slice the total proton beams, beam size, just to make the way of interacting with the electron beam. You can get more information about this on JSPEC user manual. And the force formula is messed up, but you can use a different force formula. There is also unmagnetized force formula. So this is an example of magnetized cooling, and I'm just taking Mesco force formula, but you can play with a different force formula. And another side is a ring where you need to upload some files. So you need to upload a lattice file. I'm taking 3.8 kilometer circumference RIC lattice provided by Brookhaven National Lab. So you can click in this eye and can see this lattice, which is 3.8 kilometer RIC. Beta function in X, Y, and dispersion in X are plotted. You can see individual parameter like dispersion, also, or simply this beta function in Y direction. So after that, we have to give the input for electron beam, and this gamma is 293, which correspond to 150 MeV electron beam, and transfer temperature and longitudinal temperature in EV. These are calculated from this dual energy electron cooler ring using that formula I presented before. And Bunch beam is the beam type. We use a Gaussian shape beam. We calculate the RMS size just using the formulas. Beam size simply equals to square root of emittance times beta x plus dispersion delta p over p square. And this vertical beam size using the same formula. We use this 6 centimeter same bunch length as that of proton, and we use the same number of electrons, which is 6.9 10 to the power 10, which equals the same for the number of ions. And there is a cooler section. Length of the cooler is 120 meter. You can change the length of this cooler section, and number of cooler is 1. The magnetic field in the solenoid is 4 Tesla, which is pretty big. This may be big value to make it real, but I just use this number that gives me better cooling simulation results. And also we have to introduce this beta X and beta Y for this proton beam. And we introduce dispersion of 2.5 meter in horizontal and 0.5 meter in vertical for the proton beam. For the electron beam, as I already mentioned, this is a case of the magnetized cooling. In this 4 Tesla magnetic field, electron beam undergoes lot more precision, and this dispersion is not going to affect. But in the case of the non-magnetized cooling, you have to introduce both the dispersion for electron beam and the proton beam that gives better cooling results based on some simulation done at BNL for single energy storage ring. So here, finally, we calculate the rate. This gives IBS rate, electron cooling rate, and the total expansion rate. The total expansion rate is negative, which is the combined effect of IBS rate and the electron cooling rate. It means all these total expansion rate is negative, means electron cooling rate is larger than the IBS rate, which means electron cooling time is shorter than the IBS time. Cooling effect dominates the IBS effect, so there is net cooling in all 3 directions. So this is the basic examples, how to put those parameters for the proton beam and the electron beam with the cooling section, and how to upload this proton ring lattice file. You can visualize these things going here. Here are some simulation setting. You can define the time and number of step and time step. Depends on how precise or how accurate you need the simulations. So there is a model for RMS and particle. Particle model is just how to treat. These are the model how to treat the particle in a proton beam during the cooling interaction. More details are given in JSPEC user manual. And we include this IBS effect and also electron cooling effect. And after that, you just hear this star simulation. It may take some minutes, but I already did that. So I just want to show you the results. First picture is how this ion beam emittance evolves during the cooling interaction. So I'm just clicking on the horizontal emittance, which started at 2.8 micron. You can see there is a decreasing in the horizontal emittance, not much, but it is decreasing, starting from 2.8 and going down to 2.74 during that simulation type of 72 second. Also, you can see this emittance Y, which is also decreasing by a small amount. And you can also look on this longitudinal emittance, which is dP over P. There is almost a constant, this longitudinal emittance. This clearly gives a visualization of ion beam cooling happens in all three directions. In the right side, there is IBS and cooling rates. You can look on the individual rates. So this is the combined electron cooling and IBS heating rate in longitudinal. In the same way, you can look on this horizontal electron cooling rate and longitudinal IBS rate. Also, there is a force, friction force. This cooling force is friction force which depends on velocity, and this is non-conservative force. And this shows the nature of friction force during the cooling interaction. And also at the bottom, there is a animation that shows change of ion longitudinal and horizontal the phase space during that simulation time. Oops, sorry. So there are two sections. One is the source, just to put input for cooling interaction, and you can also see visualization. So next approach is, if you click here, you can export a zip file that downloads everything, the input you have given, or you can also click here in the Python source that gives you the input Python input file. So then you can run using Jupyter in CRepo. So there is a Jupyter code already in the CRepo. So I have downloaded that zip file. I uploaded that in the folder name, which is my name here. So it has a lot of files, but one file I want to show is run.py. So when you download the Python source, that gives you a different section, which is exactly what is given here. Oh, sorry, it is not showing me. So exactly this file gives me the input I have given for ion beams. You can see this ion mass, ion kinetic energy, ion gamma. Also these normalized emittances and everything for the ion I have given in the here. Somehow I am unable to show you the source. Okay, so here, what you give here, that is exactly, you get this input file, then you can run in the Jupyter section. So it has a cooling section for the electron beam, exactly all parameter we have given in this JSPEC. Then you can go back, and JSPEC is already installed in the CRepo platform, so it is very easy to run that file. Just you write Python run that file. It creates the bunched ion beam, and it just run interaction cooling simulation. It may take a few more seconds. So it gives me the following output files, which are named as ions 100.txt, ions 0.txt. So I have written the code there that how to save my data. So I have mentioned that just save the data for is 100 interval. It is saving ions 0.txt, which is the initial proton beam phase space. Ions 1000.txt is at the end of the simulation, which is the final phase space. So I can show you how it looks like. Ions 0.txt. So it has 6 different columns: X, XP, horizontal phase space, YYP, vertical phase space, DX, DP over P, which are longitudinal phase space coordinates. So you can use your Python script or whatever just to make a plot of this initial phase space. In the same way, you can look the final phase space, which looks the same with the different coordinates. So you can use this output file to make a plot of final phase space. Also, you get the output file, which its name is STDS. So it has many columns, which is first is a time, emittance X, emittance Y, delta P over P, bunch length, and corresponding IBS expansion rate, IBS rate, and cooling rate. So you can use this file to make yourself plots of this evolution of the emittance in 3 direction and the corresponding IBS rate, cooling rate, and the total expansion rate. So this plot I have made initial and final, just taking that ions 0.txt and ions 1000.txt. So ions 1000.txt data correspond to the final, ions 0.txt correspond to the initial. In the same way here, I have made this plot using the Python script, using that JSPEC.stds file, taking the output for emittance, 2 different cases. One is without including dispersion, another is with including dispersion. So this is all about to run JSPEC simulation using Cerepo platform. So it is very easy to run using Jupyter. So I have used this for a couple of months during my PhD work in 2022. So I want to thank Steve in this platform, Cerepo platform, that became very helpful during that time. Very easy to run many simulation for a given small time interval. So I think this is all about running cooling simulation using JSPEC. So I have also given some suggestion that we need to include some parameter or some calculation in the JSPEC because there are certain things we can include and we can improve. So it is still under the process to include more effects in JSPEC. Hopefully we'll get more proton IBS calculation and also beam scattering effect in the future. But it is really a nice platform to use for the cooling simulation. I think this is the end of my presentation. So here are some references. You can go through it. If you have any question, then please feel free to ask me. I prefer to use my school email because most of this time, this pnl.gov email, may they do some quarantine and may put your email outside the organization to the spam. So please feel free to send me the email if you have any question. Thank you very much.
Thank you, Bao, and that was a great presentation. We have several questions lined up here for you, so I'm just going to start at the top and we'll tackle those one by one. So the first question is, how do you decide the values of dispersion to add to the simulation?
Yes, there is a very nice paper from Alexei Feritov BNL with nice calculation of the dispersion, of how we have to introduce a dispersion, because I already mentioned cooling is a dynamic process. You cannot get equal cooling in all three directions. So in general, you can see longitudinal temperature is very small, 0.27 eV, but the transfer temperature is order of 1,000, 9,000 or something. So there is a strong cooling in longitudinal. If we don't include the dispersion, then we cannot redistribute the cooling in longitudinal direction. So I just play with those numbers, just taking some reference from single energy storage ring cooler at BNL, and that 2.5 meter in horizontal and 0.5 meter in vertical did a great job. So I use those numbers.
Excellent, thank you. The next question we have is, do you have support for transverse coupling in the lattice? For example, coupling due to the cooling solenoid.
Yes, actually, this is a very nice question. Yeah, so when we design a solenoid in MADX or in Elegant, because I did almost this thing in a MADX and Elegant, we use this matching condition, and in that case, we use this coupling. Just we divide the solenoid into two pieces, and we use that matching condition. And yes, I think we introduced the coupling.
Excellent, thank you. And we have time for one last question today, and that question is going to be, is the version of the code on the Jupyter server the exact same as it is in the browser interface?
Yes, I think so, because I got the same results. So first I was just running the visualization, then later I talked with Stephen Coleman and RadiaSoft, and I came to know that it is easier, faster to run using the Jupyter. And already installed, I just changed those parameters in the Python file, so I don't need to change anything in these going to the server. So yeah, they are the same, I believe so.
Excellent, thanks. We've got one more question that just sneaked in here. And the question is, how do you decide the cooling rate parameters?
Exactly, we get just the cooling rate. So if I go here, it gives me the cooling rate and electron cooling rate and IBS rate. This is initial IBS rate, electron cooling rate, and the total expansion rate. So these are coming from our interaction, cooling interaction between the electron beam and the proton beam. And these are decided by those parameters. For example, if my electron cooling rate is positive, when it is not cooling, it is heating. But here it is negative, means it is cooling. If my IBS rate is bigger than this electron cooling rate, I'm just talking about the magnitude, then IBS is dominating. So these parameters are from this cooling interaction between the electron beam parameter and the proton beam parameter that determines this rate. I myself do not determine the rate. That means our electron beam temperature plays the major roles. How cold the electron beam is, how smaller those temperatures are. That's really important. So when we design the electron storage ring, that gives me equilibrium parameters that we have to try to design the ring to get the minimum emittance. That gives me the minimum temperature of the electron beam. That gives me better cooling rates.
Okay, thank you. We are out of time for today, so there are a couple of questions in the Q&A we weren't able to get to, but I encourage you to contact Baldwin at his email that he put in the final slide and go ahead and send your questions to him. And thank you again, Dr. Dattal, for being our guest speaker today, and I hope you guys will all join us for our upcoming webinar in October. Have a great afternoon.
Thank you so much.
Thanks.